Thank you all for coming out tonight. You know, it is a special night tonight for science. Who knows what I'm referring to? The anniversary. Do you know what I'm talking about? Somebody, what is it? Yes, but Light Falls is celebrating a particular event in the history of science, which was confirmation of Einstein's general theory of relativity 100 years ago today. Eclipse observations were used to confirm the prediction that Einstein made, and someone made reference. Indeed, we do have a program on tonight on PBS, so after this program, if you want more, you can run home, turn on channel 13 from 10 to 11:30. We have a program that was filmed on this very stage in February. But tonight, our focus is upon a related idea that has a deep connection to theories of gravity, our understanding of the force of gravity, because we're going to be discussing the possibility that many scientists have bought into over the course of many decades, that there's much more to the universe out there that meets the eye. And the reason that we've come to this conclusion is by virtue of studying the gravitational pulls that happen out there in the cosmos and coming to the conclusion that the stuff that we see is unable to give rise to the gravitational pull that we observe. And one way of thinking about this, just to kind of get into the subject, is to imagine that, you're flying into New York City at night. Many of us, perhaps all of us, have done this. And as you fly in at night, of course, all that you really can see are the lights in the buildings. Now, we all know when we see an image like this that there is more structure to the image, to the reality, than the lights themselves. How do we know that? Well, because we all have an intuitive understanding of gravity, and if there were no buildings, if there were no structure out there, these lights, they'd fall down to the ground. And because they don't fall, we know that there is something out there that's holding them up. And of course, by the light of day, we can begin to see what that structure actually is. And of course, we all know what the structure is. It is the architecture, the physical makeup of the buildings themselves. But without being able to see that structure itself, if we only have access to the light, which is all that we have access to when we look out to the universe, we have to infer the existence of the dark stuff that's not visible at the moment. And that's how we come to this conclusion that when we're talking about not a cityscape, but the universe, that there might be more out there than meets the eye. So this is an idea, actually, that has a long history. And I won't take you through the full history. It's a fascinating story. But I'll just give you some highlights of it. Toward the end of the 1800s, as we began to have ever greater ability to observe the night sky, scientists began to try to really understand the motion of stars out there. And one scientist in particular, Lord Kelvin, he had this idea to model the stars out there in the galaxy as if they were perhaps molecules in a box of gas. The scales are completely different, but the idea was to apply the understanding of how particles move inside of a box of gas, apply the same ideas now to stars moving within a galaxy. And when he did that analysis, he came to the conclusion that there might be stuff out there that we can't see. In fact, in his own words, he described it like this.
It is nevertheless probable that there may be as many as 1 billion stars, but many of them may be extinct and dark, and 9/10 of them, though not all dark, may not be bright enough to be seen by us at their actual distances. Many of our stars, perhaps a great majority of them, may be dark bodies.
So the possibility that perhaps the majority of stuff that's out there might be dark, this is an idea now that is going way, way back, late 1800s. And then another great mathematician, scientist, Henri Poincaré, he was inspired by Kelvin's analysis to do his own version of that analysis, and he came to a different conclusion, but he did introduce an important phrase.
Matière obscure.
He did it in French, of course, but of course that is dark matter. So this idea of dark matter goes all the way back to the late 1800s, early 1900s. And as people began to think about this idea over the ensuing decades, it's this fellow right here. Do you know who this is? Anybody know who this is? Zwicky, yeah, Fritz Zwicky, who was a Swiss-American astronomer, kind of a wonderful character. But he began to study the motion of galaxies in the Coma cluster. This is a few hundred light years away. And again, he found that the motion of the galaxies was such that it couldn't be solely due to the ingredients that he could see by virtue of their light. He concluded that there had to be additional dark stuff that was out there that would be responsible for the gravity that was pushing and pulling these galaxies around. But it was really the work of this person right here, Vera Rubin, who really cinched the case in the minds of many physicists, many astronomers, for the existence of dark stuff that's out there. Because what she did was she studied the motion of stars in swirling galaxies and found that the galaxies are swirling too quickly. The stars should be sort of ejected outward. You know, one way of thinking about this, we can do a little quick demonstration of this. You know, if you have, for instance, a very simple pedestrian situation where you have a wheel, right, and you have water on the wheel. Now, we all know, we don't have to do this, but it's sort of fun to see it. If you take this wheel and it's spinning slowly enough, very little water will fly off, but of course, you give it a real spin, and the water droplets fly right off. Thank you very much. And the idea was that the galaxies were spinning as fast as I was spinning the wheel, so that the stars should be flying off, as the water did. But Vera Rubin found that the stars are not flying off. And therefore, there had to be something else that was pulling them in, something else that's dark, because we don't see it, giving rise to the gravitational pull that was holding the galaxies together. And of course, it wasn't just pictures. There was mathematical analysis behind this. When you do the mathematics, which we won't go into any detail on, but the expectation was that the farther out you go from the center of the galaxy, the slower the stars should be moving. But in fact, her observations and analysis showed that that wasn't seeming the case. The speed of the stars out on the edge of the galaxy was too fast relative to what we thought it should be. They should be flying off, but they weren't, and therefore this notion that there should be some dark stuff that would be out there. And when you put the numbers into it, you find something rather remarkable. If you calculate the amount of dark matter that must be out there to hold these galaxies together, you find that it's 4 or 5 times as much as the amount of matter, the protons, neutrons, electrons, that makes us up. So you're talking the majority of the matter in the universe might be dark stuff. And indeed, we'll even talk about a different kind, but perhaps related, dark entity called dark energy later in the program as well. Bottom line is, the stuff that makes up you, me, and everybody else may be a tiny sliver of the mass energy budget of the entire universe. And that's a remarkable pie chart there showing us we know a lot about reality, but it might be that a lot of our focus has been on a tiny piece of the full story. Now, before bringing out the participants who will discuss this further with us, I want to mention one point that's actually related to the anniversary, the 100th anniversary of the general theory of relativity, which is this. When Einstein was doing his calculations on relativity in November of 1915, he focused his attention on a particular puzzle, a particular problem that had to do with the motion of the planet Mercury. It had been known for a long time that Mercury's orbit wasn't doing what the gravitational equations said that it should. Instead, the orbit was kind of shifting a little bit each year. And to explain this shifting orbit, some astronomers introduced the possibility that maybe there is a dark planet out there called Vulcan, a hidden planet, undetected planet that was tugging on Mercury, and that's what was causing the orbit to shift. This was the going idea until Einstein came along, and with a deeper understanding of the force of gravity in his general theory of relativity, was able to fully explain the data without any dark stuff, which is just to say that you have to have an open mind, as we'll see in the discussion going forward. Maybe there's dark stuff out there, but maybe our understanding of gravity needs to be deepened, as this historical example shows us, and perhaps a deeper understanding of the force of gravity might explain the anomalous observations. So this is a point that we will come back to. But the bottom line question that we will be discussing, is it the case that much like this cityscape, we see the light stuff, the stars, the lights in the buildings? Is there additional dark stuff out there? And if there is, what is it made of? Those are the questions for tonight, and we are fortunate to have some of the world's experts to discuss these questions with us, to illuminate these deep puzzles. So let's now bring them out. Our first participant is the director of the Kavli Institute for Particle Astrophysics and Cosmology. She's playing a leading role in modeling and mapping out tens of billions of galaxies to understand the evolution of the universe and the nature of dark matter and dark energy. Please welcome Risa Wexler. Our next participant is a professor of physics and astronomy at Johns Hopkins University and a science writer and author. His work on the cosmic microwave background, galaxy formation, and exploration of nature of dark matter. Please welcome Joe Silk. Thank you. All right, also joining us tonight is an associate professor of physics at Princeton University whose research focuses on the nature of dark matter. She has tested theories of dark matter using data from a wide range of experiments. Please welcome Mariangela Santi. All right, our final guest tonight is a professor of theoretical physics at the University of Amsterdam. His research deals with string theory, quantum gravity, black holes, and cosmology. He is a recipient of the Spinoza Prize, the highest award available to Dutch scientists. Please welcome Erik Verlinde. All right, thank you all for being here for this discussion of dark stuff out there in the universe. And I just want to begin by amplifying the point that I was making at the very end. So when we're thinking about this puzzle, that there's motion in the universe that seems that we can't explain it using the stuff that we can see using light, there seem to be two general ways of addressing this problem. It could be that there's more stuff out there than meets the eye. There could be dark stuff. And you can actually bring this up on the screen if you would, these two possibilities. But it could also be that our understanding of the forces, in particular the force of gravity, needs sort of a deeper explanation, a more full understanding, much as Einstein's general theory of relativity did that for the motion of the planet Mercury. So part of our discussion tonight will be these two possibilities, and I'll just sort of lay out the teams, if you will. So these three folks over here, I think it's fair to say you're more on the dark stuff side of the explanatory possibilities. And over there on the far left side or far right side from your perspective is Erik Verlinde, one of the most thoughtful, creative, insightful physicists that I have ever met in my entire life, so not to bias the conversation. But he has a very interesting, but I think it's fair to say speculative idea, which is more on the right side of the explanation there. So just quickly, where do you see your ideas fitting in this? Do you feel that they're developed to the point where they're a competitor to the dark stuff that will be some of the focus, or is it still very much a work in progress?
Yeah, we're very much still busy understanding gravity in a more fundamental way. I mean, there are many colleagues I do this with who are trying to combine general relativity with quantum mechanics, with using string theory. And this has developed into a new framework in which we can explain actually where gravity comes from a more microscopic picture. And I indeed believe that we can then explain these phenomena without the need for dark matter. But this is a theory that, has sort of started to become developed, but we need to do more work to eventually get the complete thing out there. So it's not like I can explain everything yet, but there's a first hint of a new theory, and then indeed you don't need the dark matter particles to explain this extra gravity that we have been observing.
And just to give a snapshot so that folks who aren't following the details of this in the research literature, is this a a minority opinion, an equal opinion? How would you sort of frame the number of people who are thinking this way versus the dark stuff explanation?
Well, it's certainly a minority, and of course I'd like to convince more people to think about it this way. I think that once we start trying to understand gravity better and have developed that theory, this will come out automatically, but this will take some time. And so it's fair to say that I'm not certainly in the majority, but there's, hopefully a growing number of people taking my point of view.
And so as we focus our attention for the first part on the dark stuff, you're going to be able to withstand this.
Of course.
Good.
I mean, I can understand even the logic for it, and so it's certainly something that's well motivated. So I can even,
Great. Okay.
Listen to that.
All right, just so by chapter 3 of this discussion, we're going to come to a focus. But let's, for the first 2 parts, focus on the left-hand side. And when we're talking about dark stuff, the natural thought that might come to mind, it's the kind of stuff that we know about. Maybe it's planets. Maybe it's stars that have burned out. Maybe it's black holes that are out there in the universe. That's sort of one collection of possibilities. The other collection is fundamental ingredients that make up those entities. Particles, perhaps the ones we know about, or perhaps hypothetical particles. So let's just start on the left-hand column here. Joe, could it be that the dark stuff is just things that we know about that are hard to see because they don't give off light?
We know about ordinary stars, and we infer from things we're going to talk about there's lots of dark matter, so could there not be dark stars? Now, we have extremely tight constraints on how much ordinary matter there could be in the universe, even in dark form, because long ago, in the first minutes of the Big Bang, this stuff was just ordinary matter, although it's now a dark star, and it did participate in thermonuclear reactions that made all the helium in the universe a wonderful prediction of the Big Bang theory, the lightest element, the second lightest element of hydrogen, and very, very abundant. And that great success tells us that the amount of this dark baryonic, dark stellar stuff, it's a small fraction. It can't be the dark matter, which then leads us to consider more exotic things. And so one intriguing possibility is the possibility of black holes that were formed very early in the universe. And so these would be ideal dark candidates because we simply can't see them. And the interesting thing is you can decide how many might be left over because they do affect light transmission from stars in nearby galaxies. They deflect the light slightly as they might pass by in front of a background star. And so this limits...
So that's like just lensing, which again, just for the historical fact, is again the very experiment that was done 100 years ago.
That's right. It's a version of Einstein's original prediction, and it's a way of indirectly inferring how many dark stars there can be. And so we're now at the point where we can set limits on the possibilities of these dark stars over a huge range in masses. And it turns out that people have studied, for example, the nearest galaxies. They've looked at stars that would be slightly affected by a passing black hole, and they can say that at most 10% of the dark matter could be in massive stars or small stars. But what is left over as a very exciting possibility are really tiny black holes, essentially the masses of asteroids, but black holes, and so incredibly tiny, but there could be a lot of them and enough of them to essentially evade all possible constraints from this twinkling effect on stars, lensing of stars. And the exciting thing about the newest data we have, which consists of staring at our largest nearby galaxy, the Andromeda galaxy, for a long time, and looking again for slight variations in star patterns. And we're beginning, there are even reports that they've found the first event that might be what they call a primordial black hole from the beginning, roughly asteroid mass. We have to take a lot more data, there could be more, but the beauty of this hypothesis is that we're not inventing any new physics.
Right.
We're not inventing new particles. we're taking known physics. We know that black holes can form. They do form, massive ones from dead stars.
And now we actually have a photograph of a black hole, so this is real
Precisely,
stuff.
That's
yeah.
right. So I think it's a wonderful hypothesis that, again, has enormous potential we're just beginning to explore.
Yep.
But if you wanted my vote on what the dark matter could be, I would put this high on the list of possible candidates. The alternative being elementary particles that we're going to discuss in a moment, left over also from the Big Bang.
Gotcha. So let's hold that as a possibility. One of the candidates for the dark stuff might be these black holes that were formed in the very early universe. But now let's turn to the other possibility that you mentioned, which is elementary particles, the stuff that makes up familiar matter, from stars to people to rocks and so forth. Now, there are a number of possibilities, but let's start real simple. Could the dark matter just be an electron? Could it be a lot of electrons out there? Could it be neutrons? Could it be protons? Could it be that kind of stuff?
Well, we're pretty sure that all this extra matter has got to be charge neutral. Because if it were electrons, we'd have electric force on one side, protons on another side. It would be a disaster. We could rule that out completely.
Yep.
Something neutral works, and something stable works. Neutrons decay. They're unstable, so it couldn't be neutrons, although they're neutral.
So 10, 15 minutes, they're gone.
Yeah, that's right. And we also need a particle that interacts very weakly with other particles. Unlike electrons and protons, which make up the stars, the Earth, etc., this dark stuff is outside the boundaries of where we see the stars. So it's a particle that interacts weakly, and basically we have to invent a new class of particles to be candidates for the dark matter. And so we do have a wonderful theory which predicts such particles. It's called supersymmetry. It postulates that very early on there were equal numbers of all types of particles, partners of each other, and the heavier partner, which had a slightly different spin, would be unstable, but the lightest of those would be left behind and could be the dark matter. That's a prediction of this very elegant theory, which hasn't been actually verified yet, but it argues for perfect symmetry in the very early stages of the universe. So it's compelling for that reason.
So you mentioned supersymmetry.
Yes.
And so this is a theory that particle physics folks come up with not to solve the dark matter problem. They introduced it for a different reason. So part of the attractive feature of black holes was that you didn't have to invent something new. It was already within the equations. So Eric, just very briefly, why do physicists, particle physicists in particular, introduce this idea of supersymmetry? And just to lead you in the direction I have, we have another program in the festival about the Higgs particle. So what's the relevance of this for that?
I mean, indeed, it's a beautiful idea, first of all, theoretically, that we can relate the particles in the standard model to their partners, but something nice happens then, namely, there's a big puzzle in the standard model, this Higgs particle that has been found. We like to understand, explain also why the mass that it has stays that value. And it turns out that if you add these other mirror particles, the supersymmetric partners, that we can explain this in a very natural way. And so the whole standard model works actually more beautifully if we add the supersymmetry. I mean, string theory actually also predicts this supersymmetry. So also from string theory, we would have been very happy to find it. Unfortunately, it has not been found yet, but the idea is still alive. And it's one of those more beautiful theoretical ideas that we hope is realized in nature.
So Mariangela, so up on the screen here, we have the left-hand side as the stuff that we've long known about, the quarks that make up the protons, the neutrons, and so forth. The right-hand side are the particles that Joe and Eric are referring to, these additional particles. Just point out the ones that we've actually seen, just so we know which ones are actually real.
Everything on the left we've seen, with the Higgs being the most recent one in 2012. And actually, this is coming back to the question you asked before, which is, of everything that we've seen, can anything actually be the dark matter? And it would be good to point out that the neutrinos, which are the ones that look like little squiggly V's,
Yep.
are probably the only thing in the standard model that has the characteristics that we'd want to be dark matter, in the sense that they're neutral and very weakly interacting, so they're not emitting any kind of light. Otherwise, we would have seen them.
Yep.
And so the trouble with the neutrinos is that you can do a calculation and ask how much of the current amount of dark stuff that's here now can be comprised of neutrinos. It's a very tiny fraction.
Too small.
Too small. So that's how we know that the standard model on its own can't account for all of the dark matter. So if we then hypothesize these SUSY particles here on the right, there are some candidates in this assortment that have the same kind of characteristics, neutral, give you the correct stability, so stable, so they give you the correct abundance today, and interact very weakly. But everything on the right, we haven't actually observed yet.
Yeah. And when I first started in graduate school, there was a going lore, which is if you wanted to write your first paper, you just make up a dark matter candidate, motivated from these ideas, and you do sort of a calculations. I don't know if you happen to have the first paper that I wrote out there. I thought it would be kind of fun to show it to you, simply because human eyes will never look at this paper again because it's just not important. It's just sort of, there it is. So it's seen the light of day. Now we can put it back into the journal and we'll never see it again. But this is the idea. So there's the possibility of exotic particles that presumably they'd be produced shortly after the Big Bang. And then how do you figure out how many of these particles would remain? So imagine the Big Bang happens, there's all this energy. What's the step? Is there a well-defined procedure to figuring out how much of those dark particles will still be hanging around today?
Yes, indeed there is. So, and it's very predictive. So what we need to know is how the dark matter particles interact with the standard model. So that's where we have to make some kind of theory assumption. But if we do that, then we can start modeling how these dark matter particles are interacting with all regular matter in the very early universe. So you might have two dark matter particles come in, interact, give you some regular matter, and vice versa. And the whole system can be in equilibrium. So the forward reaction happening with equal rate as the backward reaction. But as a function of time, what ends up happening is the universe is expanding. And so if you have two dark matter particles, at some point with the universe's expansion, they'll no longer be able to find each other anymore.
Mm-hmm.
And so
finding is important because that's how they...
Yeah, finding is important because then that's how they can interact to give you the standard
And when
model
they
states.
interact, they disappear by producing more
That's right.
ordinary stuff. Good.
Exactly, yeah. So once they can no longer find each other, then they're just, this interaction stops.
Yep.
And then however many dark matter particles are around at that point in time stays essentially constant until today, and that's the amount that we measure. So you can actually calculate what this interaction rate is, accounting for the expansion of the universe, and get a specific prediction for the amount of dark matter.
So we have a rough
present today.
version of that calculation right here. Now, of course, you don't have to understand the mathematics behind this, but the point is there is a well-defined, rigorous mathematical procedure that allows us to figure out how much of this dark stuff would be hanging around. And the wonderful, beautiful, perhaps unexpected fact is that when you do this calculation for supersymmetric particles, the typical amount that will remain for the stable ones is pretty close to the amount of dark matter that observations suggest should be out there. Now, when I learned that as a student, I was bowled over by this. I was like, of course, as many were too, it has to be the dark matter. How else could it be the case that the amount that is left over is just what we needed? Now, when you guys learned that, did you have a similar reaction, or you just sort of see this as a coincidence or something else?
I always worried it was numerology.
You were you really?
I mean, we don't have to go through these
See,
formulas.
to me, there only is numerology as a theorist, but
I mean, you're tweaking two numbers, one that's in the numerator and the other one's in the denominator, and you pick two values where it works. But what happens if you change those ratios a little bit? Then you all of a sudden open up a much wider region of the parameter space.
True, but just to push back a little bit, the natural values of those parameters, like the mass of the particle being, 1 to 100 times the mass of a proton, feels very natural. The rate at which they annihilate, that's not really put in by hand. It's using the interaction rate of the weak interact. So there's very natural choices. That still didn't...
No, I agree. I mean,
Okay.
there was an elegance to it that was compelling, but it also did... The numerology aspect of it always did make me feel a little uncomfortable.
I mean, there is this point that Mariangela made that if it's not that, the parameter space opens up a lot. And so that's an interesting situation we're in. I mean, I think it's interesting that the original papers where it seemed like, wow, that's amazing, those models have actually already been ruled out.
True.
And so now we have a much broader parameter space that we have to look at, but
Right.
yeah.
But in the old days, when this was first out there, it was just sort of an amazing thing. And that sort of drove the focus on a particular category of dark matter candidates called
WIMPs.
WIMPs. Yes, I didn't want to say it, so thank you. So WIMP stands for what?
Weakly interacting massive particle.
And the supersymmetric partners provide a class of candidates that fit that particular description and could be the dark matter.
Yeah, I mean, several of the particles that Mariangela was already talking about could be WIMPs.
So if this is a viable possibility, the key thing, of course, is to go out and find these particles. And that is something that we've been trying to do for a while. So Mariangela, can you take us through the approaches that people have put forward to try to actually capture one of these particles or create one of them?
Sure, yeah. So with WIMPs in particular, there's a three-pronged approach. So the first being, let's try to produce it in the lab. And in that case, you look at some really powerful collider, like the Large Hadron Collider, where you take two protons and you collide them together at really high energy, and you hope that in that high energy collision, you might actually be able to produce some new heavy exotic state that might be the dark matter particle.
So using the energy of the incoming particles and equals mc squared, you want to transmute that energy into these exotic folks.
That's right. And in some sense, if we can create this in the lab, that's the best scenario, because then it's in a controlled environment. We could go in and we can really study, and get at the particle physics properties of that particle.
All right. How's that going?
We haven't seen it yet. But not for want of trying really, really hard.
Right. Okay, and we're still trying, right? It's not as though the game is over, but
That's
so
right.
far,
That's
nothing.
right. I mean, the LHC has been running for the last few years, and will be continuing to run. So far, we haven't seen anything, but people are, there's going to be more data, and people are coming up with new and creative ways of analyzing it. So we never know when that surprises.
So that's one approach, trying to actually create it in the laboratory. Other approaches.
The other approach is to look for it in the sky. So to look for it in the sky.
Yes.
So if you have two dark matter particles that interact, they could sometimes, very rarely, but sometimes, produce a little flash of light.
Right.
And so you can look for this annihilation process by searching in parts of galaxies where you expect that there might be a lot of dark matter, and see whether or not there's an excess of light over what you would have otherwise have expected to see.
And how's that going?
Also, lots of data. We haven't seen it yet. Again, not for want of trying really, really hard.
and Joe, would that be your assessment?
The beautiful point of this argument is that the very same effects that stop these particles being created in the early universe still give you a value of their interactions. And if ever they could find one another, they would produce, again, a flash of gamma rays, actually, a cascade of quarks and whatever. And so the trick is, you look in the vast depths of galactic space. The volumes are so large that you can look for the accumulation of these rare events and look for gamma rays. You can see here the gamma ray sky as measured by...
Just remind us what gamma rays are, just to be...
Okay, they're photons which are thousands of times more energetic and penetrating than X-rays.
Good.
Okay, they're hundreds of MeV, X-rays are keV. So really, really hard photons produced in nuclear explosions. I mean, if ever you're unfortunate enough to be near a nuclear explosion, then you would be radiated by gamma rays. That would be one of the more catastrophic things that could happen to you. But fortunately, the gamma rays don't get through the Earth's atmosphere. We look for them from satellites in space. So, and there they can propagate freely. And so in the center of our Milky Way galaxy, which is where the dark matter mostly accumulates, you would expect there to be a slight excess of gamma rays if the dark matter is indeed the WIMP type of dark matter. And so many years ago, even before this satellite was launched to look at the gamma rays, there were hints there was an excess of something very funny going on there based on radio observations. Then when the gamma ray satellites start taking data and they modeled all the various contributions to gamma rays. For example, you get gamma rays when high energy cosmic rays hit ordinary clouds of gas. They produce gamma rays. But you know exactly where the clouds of gas are, you know what the cosmic rays are, so you can correct for all of this. And when they did this, they found that in the central degrees of our Milky Way, there's this tiny excess of gamma rays, not explainable by anything known at that time. And so straight away, the particle theorist, the dark matter addict, said this could well be the signature we've been looking for of annihilation, dark matter annihilating with itself and giving you gamma rays. And they said, well, if we take exactly the same interaction strength that's predicted from the fundamental theory, and we take the standard model, which you'll hear about in a little bit for the dark matter distribution in galaxies, lo and behold, we get the right flux. And that looked very attractive. It wasn't quite proof because there's always a bunch of skeptics around. And the skeptics said, well, look, we know there are certain types of stars. They're rapidly spinning pulsars, which the Fermi satellite also saw. And they said, well, there could be a lot of those in the center, but so faint that they're really hard to see. But cumulatively, they could give you the diffuse gamma rays. And so the jury is sort of out on one side or the other. It could be the dark matter, very elusive. It could be these millisecond pulsars. So there's a new test we can do, which we're trying desperately to do now. There are tiny galaxies going around the Milky Way, dwarf galaxies, which are full of dark matter, very few stars, and they almost certainly don't have these distracting millisecond pulsar gamma ray sources.
Right.
And so we're looking at those, staring at them with this gamma ray telescope to look for evidence of gamma rays. There are, we've looked at 20 of them. One sees the gamma rays from 1 or 2 at marginal levels, so it's impossible to say statistically whether we've found them or not. All we can say is we need bigger and better telescopes.
That satellite was built down the hall from me, and when the people were working on it, I think we really hoped that when it launched, we would sort of immediately see the brilliant signals from those dwarf galaxies.
Yep.
And that didn't happen. So, there were models that could have been WIMP versions of the WIMP, which could have had booming signals from dwarf galaxies, and we're definitely not seeing that.
Gotcha.
So we've ruled out a bunch of
But
things.
it's fair to say that this same excess that we see from the center of the galaxy, if that sort of dark matter in the dwarfs, we would be marginally seeing it now. We need bigger telescopes. That's what the astronomers always say.
So let's turn to telescopes and thinking about cosmology. So Risa, this is an area that you've spent a lot of time working on. Dark matter as a key ingredient in how the universe has evolved and how structure has formed. So let's now turn to looking into the deep sky for the signatures of dark matter. So tell us some of the approaches that have been used to figure out the role of dark matter in the formation of the things that we know about, the galaxies and other structure in the universe.
We talked already about how dark matter, if there is dark matter, if it's a particle, it's 4 or 5 times the amount of normal matter.
Yep.
So we can take that model and we can say, well, what does that predict for what happens over the last 13 billion years in the universe?
Yeah.
So that model, first, it predicts something about what fluctuations there should be very early on in the universe, which we can measure from the cosmic microwave background.
And when you say fluctuations...
I mean places where the universe is, there's a little bit of extra stuff and a little bit less stuff. So my understanding of gravity is not as complicated as Eric's. So most of what I do is just think about the same kind of gravity that you and I interact with the Earth, or the Earth rotates around the sun.
Yep.
So that kind of gravity, we can put that into our computers, and we can take the fact that there were little places in the universe which were a little bit more dense or a little bit less dense, and we can turn on gravity. And so we can actually figure out what kind of structure forms in the universe in that context.
And the idea is where it's a little bit denser, it pulls in more stuff.
Pulls in more stuff.
Yeah, right.
And where there's a little bit less stuff, you get empty regions. When you do that, you can actually make predictions also then of where the galaxies should form. And in our current theory of galaxy formation,
Yep.
one side of the screen
Yes.
Was a prediction from those simulations of dark matter and how the structure forms in a model where 85% of the mass is dark matter. The other side is actual observations, where we're actually going out and mapping the galaxy distribution.
And this is just a computer, you put
On
it
a
in
computer.
there. Yeah.
You put it in there, you see what happens. Essentially, whenever you get enough dark matter in one place, that's where you expect a galaxy to form. Basically, you get enough you get enough dark matter, then the gas can start to cool and form stars. And on the right-hand side, those observations are from a telescope called the Sloan Digital Sky Survey, which actually mapped the positions in 3D of about 2 million galaxies. Actually, later this year, we're going to start kind of the next generation of that, called the Dark Energy Spectroscopic Instrument. We're going to get about 10 times as many galaxies, and so we'll have a much better map of what that looks like.
But the point is, if looking at this beautiful video, the left-hand side, the right-hand side, they look...
They basically look the same.
Right.
Yeah, and so this is actually, what this is actually showing is that the other thing that dark matter does, so it forms that structure.
Yep.
And that structure, just like we talked about gravitational lensing with the perihelion of Mercury, just how we talked about gravitational lensing with those microlensing events, it impacts the shape of galaxies a tiny bit. So if a galaxy were round, it gets distorted.
It looks
a tiny bit. It looks distorted because its light got distorted over the several billion years that it took to get to us because there was stuff in the way.
And that stuff we assume is the dark matter, and it has an impact.
That's right. Yeah. So that stuff, if it is dark matter, actually changes the shapes of galaxies. And so the thing you're seeing here is actually a map of where all of the mass in the universe is, inferred from the positions of these galaxies. So that was a map made by the Dark Energy Survey. And actually, this map here, you're seeing, this is the first time it's been shown in public. This is 1/8 of the sky.
And just tell us what the color coding is.
So the color code basically tells you about where the mass is in the universe. So, and this is actually looking at the mass primarily about 6 billion years ago. Okay, so these are galaxies that span all the way from sort of 1 billion light years away to about 7 billion light years away. And there's, I think, about 100 million galaxies that went into making this map over 1/8 of the sky. And we're actually seeing where in the universe is there more stuff or less stuff. And by measuring how this evolves over time, we actually also learn something about the expansion history of the universe, which tells us about dark energy.
So overall, through these simulations and through the relationship to observations, you are honing an ever more precise understanding of how much dark matter there is and its distribution throughout the universe. Yeah. So this, I gather, is just adding more and more weight to your argument that the dark stuff is real and it's actually out there. So from the work that you've done, what would you say is the most, do you ever ask yourself whether the dark stuff is real, or is that just a foregone conclusion in the approach that you take in your work?
Well, on a day-to-day basis, I sort of assume it's there because it's a model that works extremely well. So we can use that model and we can make a huge number of predictions. So the things that I talked about already, it allows us to say how much there is and where it is, but it doesn't tell you what it is. So our best guess is that it's a particle, but there are other possibilities. And there could be other possibilities that give you the same distribution of galaxies, the same distribution of mass. And I think one of the interesting things is that there are clues. So the things we talked about so far are sort of looking at the universe on very large scales.
Yes.
But different kinds of particles make different predictions for what dark matter should look like on small scales. So this WIMP we talked about, it's one version of a kind of particle that's called cold dark matter, and that basically means it doesn't travel very fast.
So it's cold, it's sort of heavy, it doesn't move as quickly.
It doesn't move very quickly. And this warm one kind of moves more quickly, and the consequence of that is that it moves more quickly, so it actually erases the small stuff. And so you would actually expect in those kind of models to have fewer tiny galaxies than you would in the models on the right. And it makes lots of interesting predictions for the numbers and how they behave.
So when you compare to observation, where do the observations drive you toward? Left-hand side, right-hand side? Or?
Definitely so far to the left-hand side. So there are versions of, so the most extreme version of warm dark matter, which is hot dark matter, is, for example, Mariangela mentioned neutrinos. Yeah. So that would be hot dark matter. We've
they're incredibly light particles, that's the key thing.
And they move really fast. Right. And so all of those little clumps would be erased. And so already, so Joe was talking about the dwarf galaxies. Actually, in the last 5 years or so, we've discovered a whole bunch more tiny galaxies that are orbiting the Milky Way. There's more than 50 now. And we haven't seen gamma rays from these galaxies, but we do see that even though they're super tiny, the tiniest ones have like 300 stars, but they seem, if you look at how those stars are moving, it implies that they have like 100 million times the mass of the sun in dark matter.
Wow.
And so we've found a lot of those, and that actually kind of tells us that we don't live in a universe which is mostly warm dark matter. It could be a tiny bit warm that's like almost cold.
Yeah.
But am I right that there's still a lot of sort of missing structure? If you look at this model, it would predict many more subhalos that have not been observed yet. I mean, so there's still something to be confirmed.
These pictures here are just the dark matter. Not all of these are things that we expect to light up. So in the context, if the picture on the left is correct, then there would be a lot of dark matter, we call them dark matter halos, these clumps of dark matter. We know that in this model, that above like 10 to the 8, like 100 million times the mass of the sun, those kinds of halos should form galaxies. But below that, they're not, in this model, we wouldn't be able to see the galaxies. Now, there may be other ways to see them that we're also thinking about.
So let me ask you 2 questions along those lines. So there's a tendency in trying to address the question of what is the dark matter to think that there is a thing, a particular variety that will explain all of the dark matter. Could it be that the dark matter is a sort of smorgasbord? A few black holes, a couple of WIMPs, some other things mixed in. Could it be a melange in that way? Or is it going to be sort of one thing?
I think it's totally possible it's a melange. I mean, I think most of the time we talk about dark matter as being really simple because that's an easier thing. We want to say, is the dark matter a WIMP? Is the dark matter an axion? Is the dark matter black holes? But, we don't know.
And if the dark stuff is there, and I'll come to you just one more question before I forget it. Could you imagine that the dark stuff lives in a kind of dark sector which has its own, standard model of particle physics and has all these other things, but it has no interactions with our world besides gravity, and therefore extraordinarily difficult to directly detect because it simply passes through us without any impact beyond the gravitational force, which is incredibly weak. Is that a possibility that you pursue as well? Is that?
I think it's definitely a possibility. I think, we know that we know the standard model, which we've actually already mapped out, is very complex.
Yeah.
So in that sense, it's a little bit naive to think that the whole rest of the universe is only one thing. It's just a simpler possibility to think about.
So there could be like dark worlds, dark people, dark everything in some dark sector, right?
Well, most of the candidates we have right now for dark matter would not create dark worlds or dark people.
But I think that the dark sector models are very interesting, and with the null results that have been coming out of these experiments so far have been gaining a lot of attention over the last few years. And one of the things that's really exciting, I think, about these types of dark sector models is the types of predictions that they make are very different from the predictions that you get for WIMPs. So we have a whole slew of experiments, this massive experimental program that's been really targeting WIMPs for over the last few decades. We haven't seen it. And now, with all these new ideas about these dark sector models, people are starting to think, oh gosh, we need to start branching out and build different kinds of experiments so that we can really capture the full range of these possibilities.
And so where do things stand on heading off into that wild new territory that will differ from the focus of attention for 30 years? Is that an active area now?
It's very active, but it's also not like we're going into the big Wild West. We could do it very systematically.
Yeah.
So you can say we have the standard model, we have a dark sector, and then there's certain rules for how the two can communicate with each other. And it's a finite set of rules. So that allows us to list all of the possibilities, and then we can think about experiments that would be targeting all of those possibilities. One very natural consequence is that the dark matter particle is lighter than you'd expect for a WIMP.
So just give us a sense of scale. When we talk about WIMPs, the typical size relative to the proton is
about
what?
100 times.
100 times as much, right?
Yeah.
So when you say light, you mean?
So now we're going down to 10 to the minus 3, 10 to the minus 6 times the mass of the proton.
Right.
So considerably lighter.
So 5, 8 orders of magnitude.
Yeah, exactly. And then that has significant effects for how you look for it. Because imagine that you build an experiment where you want to look for a dark matter particle coming in and knocking into your target inside your experiment. If the dark matter particle is heavy, it'll come in and knock that target, and you'll be able to see it very easily. But if the dark matter particle is light, it'll come in and it won't knock it. And then we never see the dark matter particle, but we can see the kick to the atom inside that target.
And what sort of atoms are we imagining kicking in this?
Yeah, so this, well, a lot of the experiments are using xenon. There's some experiments using argon,
And where are
germanium.
these experiments?
So we put these experiments deep underground, so usually like underneath mountains or down in the in mines, because these signals are so faint. You're looking for these atoms just giving you a slight little jiggle after these collisions. So you need to make sure that you are sort of shielded from any other kinds of backgrounds that can mock up that type of signal.
And in this scenario, there have been signals at least reported in the literature. I don't think any of them are really believed, right? Is that the general consensus?
Yeah, that's right. The current state of affairs right now is that there's very strong limits from these experiments that exclude whatever signals were claimed by some other experiments. So the consensus right now is that those other experiments haven't been reproduced, although there's continuing efforts to try to.
And to those who have claimed positive signals, are they still supporting their previous result, or are they also agreeing that they're inconsistent with other experiments and probably are not correct?
No, they're continuing to run and continuing to stand by their original results. And it really will take repeating that experiment by a separate group using essentially exactly the same type of setup to really be able to confirm it one way or the other.
Now, if the particle is much lighter, so you're about to tell us before I interrupt you, Sarah, so if it's much lighter, then these experiments would differ in some way?
Yeah, so if it's much lighter and it comes in and it hits that nucleus, the nucleus isn't going to jiggle very much, and so it becomes really hard to see it. So, but building an experiment where you're looking for those electron recoils is different than an experiment that's looking for the nuclear recoils. And so there's a lot of brainstorming right now as to how to do that and some initial efforts to get that underway.
Gotcha. So is it a fair summary to say that there's a lot of indirect evidence for the existence of dark matter? The searches to actually find it directly are at best inconclusive, but perhaps some would even say it's beginning to close the window on certain of the favored candidates over the past, say, 3 decades. So it's a precarious situation. If it's something more exotic like primordial black holes, that would be an interesting approach, but not the one of the particle physics nature. And moreover, as we also noted, supersymmetry, forgetting about dark matter, we've looked for that at the Large Hadron Collider, and we haven't seen that either, so that window is sort of closing. So that sort of is a natural segue, at least to thinking about alternative approaches that might really stand outside the box of thinking that people have been within for a long time. So, Sarah, why don't we turn now to some of the things that you've been thinking about, which, as I understand it, begins with trying to get a fuller grasp on the underpinnings of gravity itself. And it's sort of a nice, again, day to be talking about it. General relativity confirmed 100 years ago, today, and that was, at the time, the deepest understanding of the force of gravity. You're trying to go forward from that. So just give us a sense of where you've been going in these ideas.
Yeah, so Einstein came with his theory more than 100 years ago and has been confirmed. And of course, it has also been very good in predicting things like gravitational waves, black holes, and they have been seen now. So a lot of predictions have come out and have been confirmed. But this has to do with gravity that's very strong. In particular, where we see the dark matter happening is something that where gravity is very weak. And this is where I think modifications might happen. And our understanding.
So just give us a sense of that. So when you say strong, you don't mean that gravity is intrinsically strong, you mean there's more stuff, right?
More stuff, so it's really where the acceleration is strong, and that's where a lot of matter is put together. If we look at larger scales, then the accelerations are much smaller.
Things are more diffuse.
More diffuse. Yeah. But by thinking about black holes in particular, we have learned more about where gravity kind of comes from. And this is sort of a development that started in the 70s with the work of Stephen Hawking. And with my colleagues, have been thinking about these black holes also by combining it with what we know about quantum mechanics. And then we discovered that there is actually a deep relationship between gravity and, entropy and thermodynamics. And it's from those considerations that we start seeing that there's a deeper understanding of where gravity comes from.
So can we pursue that just for a few minutes, just to give people a sense of that? So can you tell us so there's a puzzle that was raised, I guess, a long time ago by John Wheeler.
Yeah,
what was that?
So he was indeed the first person to really ask questions about, black holes, first of all. He coined the name for black holes.
On 112th Street in Broadway, actually.
Okay.
Yeah, it was. No, I'm not joking. It was at the
Yeah.
Goddard Institute for Space Studies. It was during a talk, but anyway,
So
go ahead.
black holes is where the matter is so densely packed that light cannot even escape, and there's some imaginary sphere around it that if you go beyond that, then you cannot escape anymore. We call that the horizon. And so John Wheeler asked the questions about, the laws of thermodynamics also, whether they would apply in that situation. And so he had a thought experiment where there's a cup of tea. And so this is a cup of tea, and in the tea there are molecules going around, and there's a temperature. And if you look at the motion and all the random motion of those particles in there, they represent a certain amount of entropy.
Yep.
And you can think about entropy as sort of telling you what are all the possibilities that the tea can be in. And one thing you can do is, apply the laws of thermodynamics, and then entropy always has to increase. And so he asked, does this also apply when we take a black hole in the neighborhood and throw the cup of tea into the black hole? Because what happens is that whatever it was in the cup disappears from our view, and the entropy that is in there we don't see anymore. Even if the cup breaks, we would not know it because it would go into the black hole and everything disappears. And then somehow this law of thermodynamics that the entropy has increased has still to apply. So Wheeler asked the question, where does this entropy of the black hole, where is it sitting? And so Stephen Hawking and also Jacob Bekenstein basically answered that question. And they realized that when you throw something into a black hole, that the horizon gets slightly bigger.
So the black hole eats some stuff and just gets a little bigger.
Yes, and they indeed then came with the proposal that the amount of entropy that we should associate with the black hole is actually given by the area of that horizon. And that was a beautiful idea, and they wrote down some beautiful equations for it. So this is indeed a picture of the black hole, and you can see the horizon there, and it has, so if you throw in one particle in the first black hole, the second black hole is slightly bigger, and it will have a bit more information, and this is just one little bit that has been added. So here you see the other black hole, which is slightly bigger, and we're going to compare indeed what is the amount of information in there. Squares on it, and that actually represents 1 unit of information. And this can be described actually using indeed these laws of thermodynamics, namely the mass of the black hole represents a certain amount of energy, and the entropy is then the area, and indeed the area will increase as the energy increases, and that's also the same equation that we know from thermodynamics. And now the idea comes, namely these thermodynamic laws we can really explain by thinking about the microscopic motion of molecules. So we understand precisely what entropy is. We know what temperature means, namely as a statistical measure of the energy per particle. And so we can derive those laws. But now we want to derive actually the same laws for gravity. Actually, they have the same form. And so the gravitational laws of black holes, and actually the Einstein's equations, look like the equations that the thermodynamic equations.
And that's sort of a remarkable statement, right? I mean, thermodynamics was developed in the 1800s initially to understand things like steam engines and things of that sort. And you're saying that there is a deep relationship between those laws that have nothing to do with gravity, right? They just have to do with things that we see in the world around us. And you're saying there's a deep connection between those laws and the laws of gravity.
That's correct. And this is something we have been discovering, say, over the last 3-4 decades. And in particular, the last 10 years, there's a big development trying to indeed understand these gravitational equations that Einstein wrote down from this deeper underlying description in terms of entropy.
So in principle, you could have a conversation with Albert Einstein and say, Al, the equations that you wrote down on November 25th of 1915, I can give you a deeper explanation for where they come from.
Yes, and I think that is the same way that he actually, of course, explained in a deeper way what Newton's equation was saying. And so every theory in physics that we've known about eventually will be surpassed and be sort of, well, taken over by a new theory. It doesn't mean that the old theory is wrong. It's explained at a deeper level. But there can be then circumstances where the new theory works differently. And this is where I think, indeed, when we are dealing with horizons and we can see these temperatures appearing. So one of the predictions of Hawking was indeed that black holes don't only have an entropy, but also a temperature, and that they emit, for instance, radiation.
Now that's also a remarkable statement, because normally when we talk about black holes, we don't imagine anything coming out of them.
Yes, so this is indeed the discovery of Hawking, that black holes aren't really black. I mean, black would mean that nothing can come out, but he discovered that because of this quantum mechanical properties of the horizon, they carry a temperature, and that means that they even radiate and can possibly even evaporate. And so this is all about black holes, and of course we've been talking about other things, I mean, in the universe, about even also the dark energy and what has to do with dark matter. So my idea actually indeed is that in order to understand this dark matter phenomena, it's not sufficient to only focus on that. We also have to understand this dark energy component that you talked about. I mean, the fact that we don't understand 95% of the energy in the universe, why would we focus only on one component? And I think that the dark energy is first the thing that we also have to understand more and better in a microscopic way.
So why don't we spend a split second on that, since we mentioned it, but we didn't really say what it is. So like 1998, this wonderful discovery that the distant galaxies are rushing away ever more quickly, accelerated expansion of the universe, completely unexpected.
Yes.
As we sort of see here, everybody thought that over time the distant galaxies would be rushing away ever more slowly, since gravity tends to pull things together, but it's going faster and faster. And the explanation that came out in the late 90s was there's an energy suffusing space. It's dark, it doesn't give off light, and it's giving rise to a kind of repulsive gravitational push that's making everything rush away.
Yes.
So that's this dark energy. And then so your view is that there's a connection between dark energy and dark matter.
Yes. I mean, the fact that there's dark energy in the universe has a very important consequence, namely, indeed, things keep moving away from us and even accelerating. That also means that if we look further, things are moving away faster, and eventually there will be a distance where things are moving away with the speed of light. And then you get the beautiful conclusion, namely, that acts like a horizon, namely, anything that moves faster away with the speed of light, we cannot see anymore. It's like, indeed, with a black hole, we cannot look what is inside, but now our own universe will have some horizon that we cannot look beyond. And that is happening actually in a universe that has only this dark energy in it. Then the expansion rate is actually a constant. Then what Hubble discovered, this expansion rate, can be expressed in a constant that tells you basically how large the universe is, because it will tell you where the horizon is sitting. And that horizon has very similar properties as black hole horizons. And this is where I make the connection between dark energy and the thing we talked.
So let's hear it. So the connection you draw is
the following, namely that the entropy that we talked about that black holes have, we can also associate an entropy to the horizon that our universe will have. And that horizon only appears because there's actually dark energy in the universe.
Yep.
There's also a temperature associated to that horizon. So it actually also satisfies all the laws of thermodynamics. But then you can ask, well, where is this entropy and this temperature associated to? It's actually associated to the dark energy that we've added to our universe. So I say that the dark energy is the thing we really have to understand, because that will carry also an entropy and a temperature, which is the one that we can calculate using the same equations that Hawking and Bekenstein found for black holes, but then applied to our universe.
Dark energy was essentially invented by Lemaitre. And then and discovered half a century later, it's a constant in Einstein's equations, which Einstein himself put in. But Lemaitre realized that it was due to these tiny quantum effects, and he even called it dark energy. So a constant of nature, that could be the dark energy, and that accounts for everything. It's a tiny constant, we don't know where it came from. It dominates the universe now, gives us the acceleration. But there are other constants in nature too that I don't think one is trying to explain at the moment with the unified theory. Maybe someday we will. What's wrong with that? Just saying dark energy is this constant, dark matter is some other problem.
So this constant describes more than 70% of the energy of our universe, and then we just put one constant there, while the 5% we're talking about that is ordinary matter, well, that's where all the interesting stuff happens. That's our current theory. And that's precisely what okay, so for black holes we would have said something similar. A black hole only has a mass and well, maybe it can rotate. We would not be able to explain its entropy by thinking about a black hole in that way. In order to explain that entropy, that's something we learned from string theory, we have to add many more degrees of freedom, and we have to indeed explain what's happening on the horizon of this black hole. We have to do something similar for our universe. So describing dark energy simply as a constant is making an approximation, for instance, that we can describe everything that's here in the room by just adding the temperature. And that's not describing really what's going on in the room with all the motion of the molecules that's in there. So there's a lot of things we're missing if we describe dark energy with only one constant.
But we also heard a lot of very detailed evidence, these beautiful simulations that allow us to have a video on left-hand and right-hand side, which is virtually indistinguishable, at least to the naked eye, between simulation and observation. We see these beautiful explanations of the rotations of galaxies and so forth. How far can you go in this novel approach to explaining these kinds of detailed features of the world without invoking, say, dark matter?
So what is needed to describe the observations is that there's an additional gravity that keeps these galaxies together. I mean, it's the additional pull that we want to explain. So if there's another explanation by understanding gravity better, that there is an additional pull, we can reproduce many of these results. So I see dark matter almost as a sort of placeholder in a way that we can put it extra matter there, but we're describing a fact that actually is due to the gravity itself.
So
and
when
then
it comes
all
to
these simulations would work in a very similar way if you would have an understanding of gravity that adds this additional force.
Can you talk about the swirling, the Vera Rubin, observation?
Yeah,
how would you explain that?
Okay, so there indeed I explained that I want to understand the dark energy also. And so dark energy for me has an entropy in it, but also when the matter is there, actually it has an effect, an interaction with this entropy that's in the dark energy. And we can probably show this. So indeed, this is what you talked about before. Namely, this is the expectation for these rotation curves, where on the vertical axis we have the velocity, and to the right we have the distance, and then you see the velocity going down. What's actually being observed is that it's indeed flattened. And there's an important hint in where that happens. It turns out that it happens at a moment when the acceleration drops below a certain critical value, and if we express that value numerically, we find a connection with the expansion rate of the universe, this Hubble constant. To me, that's an important hint that there may be a connection between what's happening here and what is causing this expansion, namely the dark energy. And so that indeed I can explain why there would be an additional force due to the dark energy. Here's the galaxy that's rotating, and we want to understand why there's an additional pull.
Yep.
But this has to do with the presence of the dark energy that's in there. So if we take the dark energy and add it to here, you actually will see that in this neighborhood of the galaxy itself, the dark energy has been expelled, and it tries to sort of push back again. And it's sort of the interaction between the dark energy and the matter that's there that will give the additional force that is responsible for keeping the galaxy together.
And it's more than just pictures. You're saying that mathematical analysis would...
So there is I will actually give a presentation here tomorrow at the workshop where I will show these equations. And indeed, you can work out numerically what is the additional force one expects. And you find indeed it has the correct value to predict actually even this flattening of rotation curves. This is in a particular situation. Of course, dark matter is responsible for many other things.
Yes.
Not just rotation curves of galaxies. It's used now to explain structure formation.
As we saw, yeah.
It's important for explaining what we see in the cosmic microwave background. And for that, indeed, we need to develop even the theory further so that we can also explain those things. But
so you've not done that yet, is that?
Well, there's ideas I have, but it's not like it has been worked out completely.
Okay.
But the thing that I realize is that what is needed, and this is sort of what makes these models work, is there is an extra component that gives you an extra gravitational potential, what keeps things together. But in all of those calculations, it's never essential that it's a particle. The only thing that's really used is the additional gravitational field. So the particle nature of what now is called dark matter is not essential for those things. So if I can explain the same gravitational effect without invoking dark matter, I can still reproduce many of those calculations. And the math may even be very much the same.
So what do you guys think? You know, you've been searching for these particles for a long time, haven't found them, and here's an approach that may not need them. Convincing at all, or?
Just one comment.
Yeah.
So you began, the first demonstrations of dark matter came with Rubin.
Yes.
And we saw a beautiful explanation with using dark energy, but also even before that with Zwicky.
Yes.
With clusters. And it turns out that if you apply your same theory to clusters, you do, all the attempts so far need dark matter as well. Otherwise, one cannot fit this new type of theory of a dark matter field to explain the motions of galaxies and clusters. The galaxies would fly apart otherwise.
Is that true? Do you agree with what Joe said?
So there are attempts to other attempts, you're talking about a different theory than actually the one I wrote down. Indeed, where it would have a factor that is too low. I think in my case it actually can fit the outside of these clusters. The problem really appears more in the center, where there's usually a very strong concentration of what then would be dark matter. And here I do believe that there may be other explanations that are necessary, but this is certainly a region where also supermassive black holes have been formed. There are many other things going on in the center part of these clusters, where I do think that the explanation of what's being observed there may have to do with even understanding those phenomena in a more fundamental way. So I agree, clusters still provide a challenge, certainly the central part of it. The outer parts, I think I'm pretty confident that it can be explained in the same way as I explained the rotation curves for galaxies.
So, I mean, I agree with Eric that we haven't proven that it's a particle.
Yeah.
And until we actually see evidence, of something that comes from that particle, then we won't really be convinced. But I think the thing that is so compelling about the idea of dark matter is that there are these particles that are predicted, as we discussed, for totally independent reasons. We didn't talk much about the axion. It's another particle that could be the dark matter, would behave for structure formation very similarly to the WIMP. And the thing that's so compelling to me is that you take that simple idea of, take the simplest version where it's one particle, and then you just use basic gravity as we understand it, and it makes a huge range of predictions. It predicts the cosmic microwave background. It predicts essentially the last 13 billion years of our universe, all the way from tiny galaxies to the scale of the whole universe. And it does that, in some sense, quite naturally. And you do need a new particle, but then you can make lots of predictions, and you can test them.
Right.
And we're testing them at very high precision now.
Yeah, which is why the community of physicists for so many decades has had that as the paradigm explanation. But I guess the part that feels deeply unsatisfying still is that we've yet to actually get our hands on it, right?
It's very unsatisfying.
Yep.
But, there's lots of possibilities,
Yep.
right? I mean, I really hope we figure out which one of them is right. But there's lots of possibilities, and we're just at the cusp, experimentally, of being able to test those possibilities. So I actually think that's what makes this field so exciting.
So would you say in the next, what are we looking, next 5 years, and if we had this conversation a decade from now, and assuming that funding levels stay, it's unclear, but a decade from now, how would this conversation differ?
I think we don't know. I mean, we could find it, in the next 5 years.
But I guess my question is it conceivable that we come back 10 years and we're still not sure?
Yeah.
Or would it be we've ruled out like these huge number of possibilities, and it starts to feel as though we're clutching at straws in the particulate approach to dark matter?
So my view is that the range of possibilities is pretty big. So, if we still haven't found a WIMP in 10 years, it probably doesn't mean it's definitely not a WIMP, but it means it's probably a WIMP that's hard to find. So we're definitely...
That's a great song title, man.
We're definitely, if we have this conversation in 10 years, I guarantee you we will know a lot more about what dark matter isn't.
Joe, so just speculate, 10 years from now, where do you think we'll be?
So here's what's going to happen in 10 years. And
no speculation. Right. Here's what it is.
And let me even give you 50 years, actually.
Yeah.
And so we're going to build bigger telescopes, okay? We're going to build bigger accelerators. And the reason is that China's getting involved.
Yeah.
They want to build the world's biggest, therefore the West will do something similar too. And these will be accelerators 10 times more powerful than that at CERN. That will take us to the limits of what the dark matter particle could be. We'll have new types of gamma ray telescopes. And then eventually we'll be building telescopes on the moon, which is a stable platform, no atmosphere, bombarded for billions of years by dark matter particles and other things too. A great place to start doing research too for dark matter. So I think many, many experiments, very, very expensive, but science, at some point does get done. And will get done. So and we'll discover something, even if it's not what we're looking for.
Is there, Mariangela, is there a point in your career going forward where you would say, if we cross that threshold and we haven't found the evidence for dark matter of the direct sort that we're talking about, that you would say, it's time to change perspective, either do something else or take on a completely different approach?
Well, I think we should always be keeping an open mind and investigating completely different approaches simultaneously. But I don't think that, even if in the course of my lifetime we never find the dark matter particle, that seems like a totally viable possibility to me. Because when we just simply ask in the most model-independent fashion, like let's set aside SUSY, let's set aside WIMPs, let's set aside axions, and just ask what is the range of masses that this dark matter particle can be, the most model-independent constraints that we can get are just we need the dark matter mass to be such that we can form galaxies. And the mass range is orders of magnitude. It goes from 10 to the minus 22 electron volts all the way up to black holes, right? And the WIMPs, which is what we've been spending all of our time, really most of our time really focusing on, is a tiny, tiny little sliver in that space. So in the next 5 or 10 years, I think given the amount of effort we've put in that sliver, we'll probably know one way or the other whether or not that hypothesis was viable. That's the way science works, right? You start off with a hypothesis, you pick the spot where you think it's going to be, and then you go for it, and then you say yes or no, depending on what the evidence gives you. But as we move away from that, the possibilities are so huge, and the kinds of experimental signals that you would look for in that range are so diverse that it could take hundreds of years to sort it out, unless we're lucky.
Yep. So Eric, final question. It's kind of a funny situation to be in. So you and I, both string theorists,
yes,
which famously is a theory that has no experimental evidence supporting it whatsoever.
Yeah.
And so the question that we're generally asked is, when do we give up on these ideas? And yet, beautifully, wonderfully, you're pushing in a direction that's trying to make contact with observation, but in a very unexpected way, because for so long the community has fixated on dark matter as a solution to the various problems that we've spoken about here today. So how do you reconcile that? I mean, is there a point where you think that we will have gone so long without confirming supersymmetry or finding extra dimensions or any of the other strange qualities that it's just too speculative to push on this kind of a direction? And you could just say no and we could finish the evening too.
No. I do think that the ideas we have developed there are important and they will teach us more about what gravitation is. But I do think that as a string theorist in the string theory community, we have to also ask questions that can be connected to observations. And I do think that also cosmology is one of those areas. I mean, at the moment we are working with a cosmological paradigm that uses dark matter and so on, and then is based on general relativity. But I hope that we can develop string theory to the point where we have a really this more microscopic picture in terms of a theory that combines it with quantum mechanics. And then we can also understand, for instance, the universe with the dark energy in it. And I'm convinced that once we have this theoretical framework, we can also address questions that have to do with observations. Until that time, I think we should be looking for dark matter and be having all these experiments, because sometimes you have to look and test all the possibilities before you get convinced there may be another way of looking at this. So I think we should work on both sides, where we look at observations, actually better observations even of the phenomena that are associated to it. I mean, the expansion history of the universe, what's going on in these galaxies and clusters, getting better, precision data, that will help. I mean, I hope even that there will be a time that we're going to develop the theory, our string theory, by being guided by observations, and we go back to an old time when they go hand in hand.
And we all just get along.
No, but I have certainly spent the last 10 years a lot of my time reading about what people have been looking at in cosmology and so on, because it can give me also ideas of what direction to look for. And I do think our universe is not the kind of universe that the string theorists are now studying. I mean, they're mostly interested in a very idealized model with no dark energy and which is fully supersymmetric and so on. But that doesn't seem to be describing our world. But if you want to understand what it looks like in our world, I think we also have to take the data into account.
Very diplomatic and poetic. So thank you. It's been a fascinating conversation, and hopefully we will resolve this before 50 years from now, but who knows. So please join me in thanking the group here. Thank you. So, thank you.